Okay, so it's almost the time. Thank you for coming to this afternoon session. This session is about Kleene Algebra with test, and let's welcome Cheng for the first talk, CF-GKAT, efficient validation of control flow transformations. Okay.
Hi, so I'm Cheng, I'm from UCL, and this work is mainly done when I was in Boston University. And today I'm going to talk to you about CF-GKAT and control flow validations. Did it work? Yes, nice. So the story starts with legacy applications. And in our digital life, there are some legacy applications that are sprinkled around our digital infrastructure. And a lot of them are unsupported. They won't get updates. And they are in binary form, so people cannot read it. And they are rare. Sometimes they are rarely used, so they don't receive the testing that they need. So typically, the way that we deal with legacy software is try to understand it to make sure that there is no problem with it, or we try to rewrite it using like modern software, or we even can verify it. But all of these requires to decompile the binary into a readable language, and then it will help us to understand, rewrite, and run like state-of-the-art verifier on it. So this raises a problem of the correctness of the decompilation process. And in this work, we are focusing on one particular stage and one particularly complicated stage of decompilation called control flow restructuring. And control flow restructuring is basically the process of turning a control flow graph or a goto program into a program with while loops and the normal programming feature that we can actually read. So this is a very active research area, and people are continuing to output algorithms, new implementations here. And this is one screenshot from a paper at USNIX, and there's a little 4 here that was supposed to show but covered. So this is 2024, so it's very, very recent. So as we can see, this is an ever-developing field. And for this work, we don't want to design a validator for the decompiler of yesterday. We want a generic algorithm that can work for the decompiler of tomorrow. And we want it to be powerful. We want it to not produce false results, both false positive and false negative, and that's a very big goal, and it can only be achieved by understanding what are the properties that they want to satisfy. And finally, we want this to be automated and very efficient so that we can put this in decompiler and the programmer can enable an option to run this verification every time they do a decompile to add a little bit more correctness guarantee to their decompilation process. And before I introduce our algorithm, our semantics, it's important to understand what are the current techniques used in control flow restructuring. So here is a particular control flow diagram. It has 2 states, L and R, and the starting state is the left state. And the left state under condition B will execute P to R, and from R it will exit if condition B also holds, and also in reverse. So this is one way to turn this into a while loop program. Sorry for flushing you with code, but I will explain that. So we introduce a new variable, x, and this is what we call an indicator variable or dummy variable. And x basically keeps track of which state the current execution is. And x starts with L, and then we iterate through the automata. In these 2 red conditions, they correspond to transition. As you can see, when the current state is L and B is true, we execute P. And then we set x equal to R to indicate current state is changed to R. And similarly, these 2 conditions represents halting by setting x into halt, and it will exit the loop and terminate. So this is a very naive implementation of the restructuring. In the real world, it's much more sophisticated, but in the real world, they also use indicator variable in similar ways. A perhaps more clever way to reconstruct this is by using the structure of the loop and break out of the loop when necessary. So we can see like there are primarily two ways of doing control flow restructuring. First, they would use break, continue, return, things like that, which we call non-local control flow. Second, they use indicator variables. And another important thing to realize is that the correctness conditions are almost always guaranteed by trace equivalence, in the sense that under the same condition, they will execute the same command for both programs. And whenever you see trace equivalence, you should think Kleene algebra. If I ever start a cult, I would let all my cultists to say Kleene algebra every time people mention trace equivalence, because starting a cult is fun. And in particular, we choose guarded Kleene algebra with test, which is a variant of Kleene algebra with test. And the reason is that it's very fast to validate equivalence within guarded Kleene algebra with test. However, guarded Kleene algebra with test is very bare-bone. This means that it has no support for indicator variable. It has no support for non-local control flow. Well, what do? We just add it, right? This is not the first time we extended Kleene algebra. What can go wrong? So the syntax is rather simple. We have the theory of guarded Kleene algebra with test providing us with if statement sequencing while loops, the normal while program. And we add indicator variable or dummy variable. They basically only can be assigned from a finite set of constant value. So you cannot do x equals to x plus 1, and they can only be tested against the current value of x. And we also add non-local control flow, which includes break, return, and in particular, we also include label and goto. The reason is, in order to prove the control flow restructuring is correct, we actually need to compare the program pre-restructuring and post-restructuring. And the program pre-restructuring are control flow graphs, which are typically represented as goto program. So goto and label are very essential in this system. So now we encounter our first problem. We realize that the trace semantics cannot record the indicator value. Why? Because if we look at the original program that we have using indicator value to do the control flow restructuring, comparing it with the goto version of the program, which represents the control flow graph, one of them has the indicator variable in there, but the other one doesn't. This means that if we record the indicator, the value of the indicator variable, these two can never be equal, right? However, if we don't record the indicator variable, it causes problem in composition. If we want to define our semantics inductively, we necessarily need to, when we compute the composition, we necessarily need to compute the first and then compute the semantics of the second. And notice the first cannot record the value of x, but the second needs to depend on the value of x. So this doesn't work. Another challenge is non-locality. For example, what should the semantics of break be? In a normal program, we all know what the semantics of break is. Break will simply exit the loop and execute Q in this case. But to define the semantics inductively, we necessarily need to consider the semantics of break in a vacuum, which is very confusing. Similarly, it's also very confusing to think of the semantics of goto, because we don't really know what goto will do until we know what label L will do. Turns out both of these problems can be solved by introducing an intermediate semantics, which we call continuation semantics. Continuation semantics does two things. It records the ending indicator value. For example, in here, the semantics of x equals to 1 under the starting indicator value I, it will say, under any condition, which we represent using alpha, it will halt and output indicator value 1. And by halt, we denote halt by accept. And similarly, for non-local control flow, a goto-L will simply be resolved into a continuation jump, which says under any condition, we will jump to label L and starting with I. So notice that the jump here is merely syntax. It doesn't have any semantical meaning, and we will resolve the semantical meaning later. And then we can obtain our trace semantics, or we call guarded language semantics, from the continuation semantics. In the indicator value case, we simply remove the ending indicator. We no longer needed it because we have already computed the semantics of the entire program. We no longer need to compose anymore. And for the semantics of goto-L, we will resolve all the jump continuation by replacing it with the semantics that computed starting from label L. So by introducing the continuation semantics, it kind of gives us a breathing room so that continuation semantics can be defined inductively, and then we can lower it into the guarded string semantics, which is the actual trace semantics that we want. Okay, so that's the denotational semantics. What is the operational semantics? We first introduce an operational model, which we call CF-GKAT automata, which is very similar to control flow graph that I have demonstrated before, or GKAT automata, which is basically the same as control flow graph. So you notice instead of, when transitioning from state to state, instead of saying, oh, under condition B, I will execute P, I also record the starting and ending indicator value because they are important. And from a state, under a condition, instead of just halting, it can also output a continuation like jump. And for each label, we have a special state to represent the entry point to tell the automata how to enter from that particular label. In this case, you can only enter the automata when you start from indicator value 3 and condition C holds. Then you will execute Q and you end up with indicator value 5. And if we simply trace all the commands and the conditions that the CF-GKAT automata has, we can get the continuation semantics from there. And similarly, like lowering continuation semantics into guarded language semantics, we can also lower CF-GKAT automata into GKAT automata, simply by pushing the indicator value into states so that we are no longer tracing the indicator value. They are part of the state now. And we are connecting all the jump with their corresponding entry point. And this is the result from the original GKAT paper. If you trace the condition and action of GKAT automata, you get a guarded language semantics. And we proved that this square commute in the sense that if you compute the semantics first and then lower, it's exactly the same as lower first and then compute the semantics. So this is a very nice correspondence we get. So at this point, we have the domain of the operational semantics. We actually need to define the operational semantics. That is, how does for each expression or program, we need to give a certain automata in the domain. And this is through Thompson's construction, which is very similar to the original Thompson's construction proposed for GKAT. And finally, we proved the correctness of this Thompson's construction by showing that the continuation semantics of the CF-GKAT program and the CF-GKAT automata coincide. That is, this triangle commutes. If we compose it with the previous commuting square, we get a very nice picture. You might not believe me, but I will show it. If you go from the top, this is basically doing like operationally. So you compute the operational model, you lower the operational model, and then you trace the operational model. So this gives you the operational semantics. This gives you a semantics to compute operationally. And if you go down, it gives you a semantics to compute denotationally. And this, the commuting of these two this triangle and this square means that the operational semantics and the denotational semantics of our program coincide. So that's a very nice property. But beyond that, it's even nicer because in the original GKAT paper, they proved that guarded language semantics has a very strong correspondence with GKAT automata. Specifically, for any two GKAT automata, they have the same semantics if and only if they are bisimilar. So this gives us a way to construct a correct algorithm. For example, if we given to CF-GKAT program, we can simply compute their automata using Thompson's construction and then lower it into GKAT automata, and we run bisimulation, then we obtain their equivalence. And because of the correctness of GKAT automata, we get our correctness for CF-GKAT program, that its decision procedure will return true if and only if input programs are trace equivalent. So we produce no false positive and no false negative with respect to trace equivalence. And finally, the conclusion is that we give intermediate semantics, we give operational semantics, respectively using continuation semantics and CF-GKAT automata. And we prove the equivalence between our operational and denotational semantics. And we give a correct decision algorithm. And finally, we implemented we constructed a prototype implementation. We send some particularly nasty function in core util into there. There are nested loops, there are gotos in the original program, and when we compile and decompile that program, we can barely recognize it from the original program. They added like 3 more gotos in the original program, and turns out if we run our validator on it, it can validate it in like half a second. So our implementation is pretty good. So some future work. Our implementation is pretty good, but it can be improved. We can use some symbolic algorithm to speed up the implementation. And we can integrate with existing compilers so people can actually use it. And we are also working on equational axiomatization. It's pretty hard, but I think I have an idea how to do it. But I said it about my previous 5 attempts, so I don't know. And we are trying to do a graphical axiomatization. It's because in a lot of these algorithms, they actually do graph algorithms on the control flow graph. So for example, they are finding cycles with the control flow graph. They are saying if there's an exit of the cycle, then do this. So it seems like a graphical axiomatization, a graphical proof theory, it's kind of necessary in this domain. And for current progress, I made some friends with string diagram people. And just as a proof, we all love proofs. This is Wojtek Rozowski, and this is Leo Lobowski. And I didn't have time to take a selfie with Rolf Sarsky, and he sent me this. And I didn't have time to add myself in there, but just to tell you, I actually have friends. And questions? Hi.
Okay, thank you for great talk. So I think we can take only 1 or 2 questions first.
Nice talk. So since you're showing Wojtek and Ralf.
Sorry, give me a microphone.
Since you're already showing.
You're turning down.
Yeah. Since you're showing these guys who are working on probabilistic systems. So do you know or think that your full abstraction result would apply to probabilistic Kleene algebra as well?
Yeah, so guarded Kleene algebra with tests has a probabilistic model, but I don't see like probability used in very non-trivial way in the decompilation algorithm. So I don't know if we have a dedicated probabilistic system for it, but I think our system can verify probabilistic systems. So it's within the semantics. Yeah.
Okay, so any more questions? Okay, so if you have no questions, I have one.
Oh, please. Okay.
So I want to know, so I know we can remove the continue and break without counter semantic. So why do you include them in your semantic? And also, since we are going to model in the value of variables, have you considered using abstract interpretation?
Sorry, can you reiterate about continue and break?
So I know that we can remove that without harming the program semantic. That's just semantic sugars, right?
Oh, no. Oh, yeah, right. So the reason we include these kind of non-local control flow instead of doing everything using goto is because that's what we are actually verifying, right? Yeah. So we are verifying that control flow transformations, which means that, say, if you replace a loop with goto, it's actually correct. So, and if we have this kind of goals, replacing everything with goto seems like counterproductive. That's the reason.
Okay.
Does that make sense?
Okay,
yeah.
Thank you for
answering.
And
we haven't done abstract interpretation, sorry.
Okay, okay, thank you for answering. So let's thank Cheng again for his great talk.